Stop. Look at that number. 25%. That's the average hunt success rate of a lion, the animal the entire world decided was the king of predators. Now consider this. A dragonfly succeeds 95% of the time. A wild dog, 80%. A mantis shrimp, it can kill with a miss. You've been taught that the apex predator is the biggest, the fastest, the most aggressive. That's the story. That's what every nature documentary sold you. It's wrong. The predators that truly dominate, across millions of years, across every environment on Earth, don't win because of raw power. They win because they run a system. A logic so refined it looks like instinct. But it isn't instinct. It's something colder, smarter, more calculated than anything a single trait could explain. These 5 predators figured it out, and once you see how, you'll never watch nature the same way again. One of these 5 can make a decision before its own brain registers the threat. It doesn't react. It preacts. That shouldn't be biologically possible, and yet the data is undeniable. By the end of this, you'll understand exactly how and why it quietly dismantles every assumption about what intelligence actually looks like. The African wild dog weighs about 30 pounds. The lion, 400. Same savanna, same prey. The lion should win every time. That's how size works, right? Except the wild dog succeeds on 80% of its hunts. The lion, 25%. This isn't an anomaly. It's been documented across decades of field research, most recently confirmed in a 2020 meta-analysis published in Mammal Review tracking thousands of hunts across sub-Saharan Africa. So what's actually happening? Wild dogs don't chase, they compute. Each dog in the pack tracks a different variable simultaneously: prey fatigue, terrain gradient, wind direction, escape routes. No single dog is directing this. The system is distributed. It self-organizes in real time. What looks like a pack of animals is actually a mesh network running a live optimization algorithm. The lion is powerful, the wild dog is efficient, and efficiency, compounded over time, makes the lion look ordinary. But efficiency has a weakness. It assumes the environment is predictable. What happens when it isn't? The octopus has no skeleton, no armor, no claws. Its body is essentially a soft bag of organs with arms attached, and yet it hunts prey twice its size, regularly. The reason breaks almost every rule of how we think about predator biology. 2/3 of an octopus's neurons are not in its brain. They're distributed across its 8 arms. Each arm processes information independently, sensing, reacting, problem-solving, without waiting for central authorization. A 2021 study from the Hebrew University of Jerusalem confirmed that octopus arms can navigate complex physical obstacles and manipulate objects while the central brain is occupied with an entirely separate task. The octopus doesn't multitask, it multiprocesses. In practical terms, it can simultaneously camouflage its entire skin, reach one arm into a hidden crevice to extract prey, and track a second target with its eyes, as 3 completely parallel, independent operations. No bottleneck, no delay, no single point of failure. This is why it's virtually impossible to trap an octopus using conventional logic. You'd have to outsmart 8 semi-independent decision-makers at once. But raw cognitive power still isn't enough if your timing is off. Because in nature, being right 0.1 seconds too late is identical to being wrong. A dragonfly succeeds on 95% of its hunts. That number doesn't exist anywhere else in the animal kingdom at comparable scale. It's almost statistically impossible, and it has nothing to do with speed, strength, or size. Dragonflies don't chase prey, they intercept it. Every other predator reacts to where the prey currently is. The dragonfly calculates where the prey will be and flies directly to that coordinate. It's solving a real-time geometry problem in mid-air, in milliseconds, with a nervous system the size of a grain of rice. A 2012 Harvard study used high-speed cameras to map this in frame-by-frame detail. The finding? Dragonflies deploy a form of selective attention previously thought exclusive to primates. They lock onto a single target among dozens of moving objects and filter out all other visual data entirely. The result is a targeting system, not a hunter. What makes it untouchable is the combination: predictive trajectory calculation, plus selective perceptual focus, plus a body capable of micro-adjustments at speed. Remove any single component, the entire system collapses. This is the pattern emerging across all 5 predators. It's never one variable. It's always a stack, but there's a predator that takes this stack further than anyone else by eliminating the most expensive cost in any decision. Time. The mantis shrimp strikes at 50 miles per hour. That's fast enough to generate a cavitation bubble, a shockwave in the water that collapses with the force of a small explosion. It can stun prey even when the strike physically misses. It can kill with a miss, but the speed is almost secondary. What matters is where the decision happens. The strike command doesn't travel to the brain for processing and back down for execution. It fires from the spinal ganglion, a local neural cluster. The brain receives information about the strike only after it's already complete. The mantis shrimp has outsourced its fastest, most critical decision to a system with zero cognitive delay. Pair that with eyes containing 16 types of photoreceptors. The human eye has 3. And you have a predator operating in a sensory dimension its prey literally cannot perceive. You can't defend against a threat you can't detect. You can't react to a strike that ended before you registered it began. That's not power, that's architecture. But there's one predator left, and it doesn't use speed, or distribution, or geometry. It uses something far more unsettling. Patience engineered into its biology. The trapdoor spider doesn't hunt. It waits. And it has turned waiting into the most lethal strategy in invertebrate biology. Buried beneath a perfectly camouflaged door, silk, soil, and debris fused into an invisible hinge, it sits in near-total sensory isolation, motionless, sometimes for hours, but it isn't passive. It's reading vibrations. The trapdoor spider uses a network of silk tripwires radiating outward from its burrow entrance. Each thread is calibrated to transmit a different type of vibration: footstep weight, frequency, rhythm. The spider processes this data in real time from inside the sealed burrow, building a picture of the surface above without ever exposing itself. A 2018 study from Murdoch University in Australia found that trapdoor spiders can distinguish between prey vibrations and environmental noise, wind, rain, falling debris, with remarkable accuracy. When the signal matches, the door opens in under 300 milliseconds. The prey is gone before it registers danger. Zero pursuit, zero energy spent, zero exposure. Every other predator on this list exerts. The trapdoor spider conserves and strikes with surgical precision only when the probability of success is near absolute. It doesn't hunt more efficiently than the wild dog. It hunts less and wins more. 5 predators. 5 completely different systems: a distributed network, a multi-processing body, a geometry engine, a precognitive strike mechanism, an invisible ambush built on vibration data. None of them rely on a single advantage. All of them run a stack, layers of cognitive, sensory, and physical tools operating simultaneously. And none of these systems were designed. They were iterated across millions of years of failure, pressure, and refinement. What you're watching when these animals hunt isn't raw nature. It's the compressed output of an optimization process longer than the human species has existed. Evolution doesn't build predators. It builds solutions. And the ones that survived aren't the ones that hit hardest. They're the ones that asked a better question. The dragonfly didn't ask how to chase faster. It asked how to eliminate the chase entirely. The trapdoor spider didn't ask how to find more prey. It asked how to make the prey come to it. What question are you asking? If this changed how you see predators, subscribe. There's an entire world of hidden logic we haven't touched yet. Drop a comment. Which of these 5 hit you the hardest? And if you watched this far, the like button is right there.